Show that the limit as x tends to infinity of 1 plus k over x all this raised to the power x is equal to e raised to the power k, where k is a non-zero constant. That means k belongs to the set of real numbers and k is different from 0. For us to show this limit, we are going to make good use of this property. We know that for a belonging to the set of real numbers, e raised to the power ln a is equal to a. It simply means if we take e raised to the power ln 1 plus k over x, all this raised to the power x, this will simply be equal to 1 plus k over x, all this raised to the power x. That is what it means. For us to get this limit, it simply means the limit as x tends to infinity of 1 plus k over x, all this raised to the power x, it will simply be equal to the limit as x tends to infinity of e raised to the power ln 1 plus k over x, all this raised to the power x. This will simply be equal to the limit as x tends to infinity of e raised to the power, applying the law of power, this will give us x ln 1 plus k over x as such. Now, by applying the properties of limits, this will simply be equal to e raised to the power, the limit as x tends to infinity of x times ln 1 plus k over x, by applying the properties of limits. X is the same as 1 all over x. That means if you take the reciprocal of 1 over x, it gives us x. We are going to replace this x here with the reciprocal of 1 over x. This will simply be equal to e raised to the power, the limit as x tends to infinity of ln 1 plus k over x, all over 1 all over x. This is what we are going to obtain. Now, for us to get this limit, we need this limit, the limit as x tends to infinity of this quotient of two functions, ln 1 plus k over x, all over 1 over x. This will simply be equal to, by direct substitution, this will give us the ln of 1 plus k over infinity all over 1 all over infinity. This will simply be equal to the ln of 1 plus k is a constant, a non-zero constant. We are dividing a non-zero constant by a very, very, very large number. So this goes to 0 all over 1 divided by a very large number gives us 0. It turns to 0. So this will simply be equal to the ln of 1 plus 0 gives us 1 all over 0. and this will simply be equal to the ln of 1 gives 0 all over 0, which is the indeterminate form. That means from this we can draw no conclusion about this limit. That means we have to apply other techniques of getting limits. For us to get this limit, we are going to make good use of L'Hopital's rule. And L'Hopital's rule states that for us to get the limit of equation of two functions, the limit as x tends to infinity of the equation of these two functions, g of x over f of x, such that by direct substitution, this gives us the indeterminate form, that is 0 over 0 or infinity over infinity. Then this limit will simply be equal to the limit as x tends to infinity of g prime of x all over f prime of x, where g prime of x is the derivative of the function g of x and f prime of x is the derivative of the function f of x. We are going to apply L'Hopital's rule to get this limit. It simply means the limit as x tends to infinity of ln 1 plus k over x all over 1 all over x will simply be equal to the limit as x tends to infinity of derivative with respect to x of ln 1 plus k over x all over the derivative with respect to x of 1 all over x. Next, we have to differentiate these two functions so that we can easily find the limit as x tends to infinity. First, we have to differentiate the ln of 1 plus k over x with respect to x. This will simply be equal to, we are differentiating a logarithmic function, and the derivative of this function will simply be equal to, we differentiate what we have in brackets with respect to x all over what we have in this bracket, which is 1 plus k over x. This will simply be equal to the derivative of what we have in this bracket will simply be the derivative of 1 gives us 0 plus the derivative of k over x. K over x is simply the same as k times x raised to the power negative 1. Differentiating k times x raised to the power negative 1 simply gives us negative k x raised to the power negative 1 minus 1, which is negative 2, all over 1 plus k over x. This will simply be equal to, keep negative k at the numerator, we send down x squared times 1 plus k over x. This will simply be equal to negative k all over, we have to multiply all through by x squared plus x squared times k over x is simply gives us kx. So this is the derivative of the function we have at the numerator. Now let's differentiate the function we have at the denominator. D over dx of 1 over x is simply equal to d over dx of 1 over x can be expressed as x raised to the power negative 1. And the derivative of x raised to the power negative 1 is simply equal to negative x raised to the power negative 1 minus 1, which is simply equal to negative x raised to the power negative 2. And this is simply equal to negative 1 all over x squared. Gives us this result. Knowing the derivative of the numerator and the derivative of the denominator, it is very easy for us to find this limit. The limit as x tends to infinity of ln 1 plus k over x all over 1 over x is simply equal to the limit as x tends to infinity of the derivative of this function we have for the numerator, which is negative k all over x squared plus kx. Divide this by the derivative of the function we have for the denominator, which is the derivative of 1 over x, which gives us negative 1 all over x squared. This is L'Hopital's rule. Next, we have to simplify, then we find this limit. This will simply be equal to the limit as x tends to infinity of negative k all over x squared plus kx times, we have to invert what we have at the denominator. It gives us x squared all over negative 1. This will simply be equal to the limit as x tends to infinity of negative k times x squared. It gives us negative k x squared all over x squared plus kx times negative 1. It gives us negative x squared plus kx. We are dividing a negative numerator by a negative denominator. It becomes positive. It gives us the limit as x tends to infinity of kx squared all over x squared plus kx. This will simply be equal to, we are going to factor out x squared at the denominator. It gives us the limit as x tends to infinity of kx squared all over x squared times 1. X squared times 1 gives us x squared plus x squared times k over x gives us kx. This will simply be equal to, at this level you see that x squared at the numerator will strike off x squared at the denominator. So this will give us the limit as x tends to infinity of k all over 1 plus k all over x. At this stage, we are going to insert x equal to infinity. This will simply be equal to k all over 1 plus k all over infinity. K over infinity gives us 0. That means we are dividing a non-zero constant by a very, very, very large number. So this goes to 0. And this will simply be equal to k all over 1 plus 0, which is simply equal to k all over 1 plus 0 gives us 1. This is equal to k divided by 1 gives us k. It simply means this limit is equal to k. E raised to the power the limit as x tends to infinity of the ln of 1 plus k over x all over 1 over x is simply equal to e raised to the power, this limit gives us k, e raised to the power k. It simply means this limit is equal to e raised to the power k. Is the limit as x tends to infinity of 1 plus k over x, all this raised to the power x, is equal to e raised to the power k. We conclude, therefore, the limit as x tends to infinity of 1 plus k over x, all this raised to the power x, is equal to e raised to the power k. Take note of this. It is very, very important. Let's take an example, e.g. we are to find the limit as x tends to infinity of 1 plus 5 all over x, all this raised to the power x. It will simply be equal to, if you compare this and this is 1, k is 5, x remains x. So this limit will simply be equal to e raised to the power k. Our k is 5. So this is an example of how we make use of this formula. We are done with the solution of this question. If in case you have any doubts, feel free to leave your questions at the comment section. Please like the video, share, and subscribe to this channel. Thank you very much for watching.